All right, so first, I'll just go over the homework problem. I'll just reread what the problem is. So we wish to maximize a loss function, criterion L, in a deep network, where each layer of a neural network models a functional mapping f of I from x and wi to y, with x, wi, and y being tensors of order d, n, and m. Assuming x maps to y, we wish to compute the following loss function. All right. So all right. Okay. All right. We want to compute the generalized Jacobian, which is also denoted as dy dx. The generalized Jacobian is generally too large to fit into memory. How can we compute dl dx without the need to explicitly calculate the Jacobian? So we're going to assume f of I is a linear function. So by this definition, when I think of a linear function, I'm just going to assume w times x. Some of you might have switched it around or added a bias term, but when you're computing the gradients, that constant term is just going to cancel out. Okay, so it's kind of difficult to work all the way up from just starting right to tensors from an arbitrary dimension. So one thing that might be of use to you guys is to just start from a scalar, right? Mapping a scalar to a scalar. So let's just assume that this is a scalar, this is a scalar. We'll call this y, and this is also going to be a scalar, right? Easy enough. So if we wanted to compute dl dx, first ask yourselves, what's dy dx? All right, so by definition, dy dx is just going to be equal to w, right? Pretty straightforward, right? And then when we're computing, assume we previously computed dl dy, we can call that just some value delta, right? Fairly straightforward, all right? And then if we wanted to concatenate or multiply these two together, basically we're just left with the following. Fairly straightforward, right? Shouldn't be difficult. Okay. Now, so this is scalars to scalars, all right? Where these are both scalars. So how do we map vectors to vectors, right? So by this definition, supposing we have an output of, no, so that's not what we want. Supposing y is a vector and x is another vector, and then this is some matrix, so let's find that. So if we define f of x is equal to y, where y is an element of R, say M, and then x is an element of R, say N, right? And then W is going to be a matrix of R. So we got rows, so N, and then is that right? No. Other way. Yes, you want your output to be column. All right. So we can visualize this. I like to think geometrically. So this is y1 all the way to yn, and then this is going to be equal to our weight matrix, right? So this is going to be w11 all the way to w1n, and then we go all the way down. So wn1 all the way to right? X1. Oh, no. Yeah. Pretty straightforward, right? Just the standard matrix multiplication. Right? Any mistakes? You guys see anything? Okay. So we want to compute what's the analog to the derivative of a vector mapping to a vector. What is that? It's a Jacobian, right? So what we can do is we can compute the derivative with each element, with respect to each element, right? So again, each element dy. By the way, what's the size of that Jacobian? What's the size? Anyone want to guess? Right, it's gonna. I think should be the same size as that, right? All right. All right. So say this is some entry in that Jacobian. Just for notation purpose, make it clean. Right? What do we got to do? All right. Before we do that, let's compute what each entry will be in the output. All right. So what we can do is we can just take some particular row and then multiply that column and just do the dot product of that, right? So y I is going to be equal to W, so this is going to be N, Wi, J, X, J. All right. Now, is that right? When we're computing the derivative with respect to some particular, let's make this k, actually. K equals 1, just so we're not going to get confused. Okay. When computing the derivative with respect to x, j, what is this going to give us? All right, so it's just a linear combination. So if you compute the partial derivatives with respect to dxj, all you're going to be left with is wij. And fairly straightforward. All right, great, awesome. So now we know what each of these elements are going to be. Okay, that define that matrix, the Jacobian matrix. Fairly straightforward. Okay. So when we're computing the gradient, gave the answer away. When we're computing the derivative of our loss function with respect to y, what is that going to give us? What's the analog of the derivative of that? Is that going to be a Jacobian, or is that going to be gradient? Gradient, right? So if I compute dl dy, this is a scalar, and then this is going to be a vector, right? So this is going to return dl dy 1, dl dy 2, and so on and so forth, right? Pretty straightforward. All right. Or I think to make the matrices work, I think you're going to have to transpose them. So basically, dl dx is going to be the product of the two, dy times dy dx, which is, if I were to draw this out, dl dy y1 dy n, and just multiplying that by that other matrix. Okay. All right, so pretty straightforward. Now, when we perform this matrix multiplication, what are we going to get? So this is going to be big, right? We don't want this to be big. But if we multiply these two together, or create some kind of object where all we're returning is just the product of the two, the dimensionality is going to be significantly smaller. Pretty straightforward. When you guys are inevitably designing PyTorch 2.0 after you graduate here, or TensorFlow, or the next generation of Keras, you got to make sure you're understanding how to represent objects that aren't necessarily computationally expensive in terms of memory or just the length in computation in terms of time. All right. So if we do this, then we can find that this, for each element, is just going to be equal to k equals 1. So we could call this delta y. Delta yi k times wk j. Right? That defines this summation. I'll write it again, just to make sure. So dl dx j, it's just going to be n k equals 1 sigma y, or delta, sorry, I k times w k j. Good? All right, so that's each entry. All right. Now, where do we go to make this work for any arbitrary tensor? So for the past week, I just tried my best to study how to multiply two tensors, like the formal method to multiply two tensors. And I was looking at how to compute circulants and how to technically unpack multiple layers of these tensors such that you can actually perform some kind of computation. And before I inevitably or inadvertently tell you something that's incorrect, what I thought would be more appropriate is just to tell you what I would typically do if my dimensionality was quite large and I was actually applying this to a neural network. So suppose we have an image, right? So conventionally speaking, what would an image be represented as? What's the order of that image? Assume we have a color image. Does anyone know?
RGB image.
Yeah, so it's an RGB image. So what would be the shape of that? Right. Right. So assume okay, you're on the right track. So you have an image. What would that mean? So say you have, say you got n pixels to define the height, n pixels to define the width, and then we can add another dimension right over here. Okay. Where each of these define the color channels of red, green, and blue, right? So this is just a simple third order tensor, right? Now, if you're applying like a deep network to process, say, videos for like action analysis, you're going to be working with a sequence of these, right? So you're going to be, you can think of stacks or vectors of tensors, if that makes sense. If you're, then you can add another dimension and making your life even more complicated if you have a mini batch during training for like stochastic gradient descent. That would require you to do, add another dimension of say n, or a big N, which is the number of samples. So it gets messy real quick, right? Now, supposing we're just doing image classification, typically what we do is, again, we'd be applying some kind of filter if you have a convolutional filter in 2D. Okay, so assuming we're training, we have n of these samples, so you can just assume that I have n of these. If I were to define another tensor that defines the convolution, say, just assume this is like a 3 by 3 convolution. What this is going to do for one convolution is that it's going to be an element-wise product on that tensor, right? So basically, I'm taking this, I'm doing an element-wise product on each of these sets of the subsets of the tensor, and then I'm sweeping that across. And each time I do an element-wise product, I return. I don't know if it necessarily that would return if you take the norm or the summation of all those elements from that element-wise product. That would return the output of that convolution. Pretty straightforward, right? Yeah, I mean, any of you guys worked with neural networks before? Or for the most part, yeah. Most of us have tinkered around with Keras or TensorFlow or any of the MATLAB demonstrations. So we're all fairly well versed with that. Now, so you have typically you have multiple of these filters, right? Right. You apply them, and then you get another. This will return another tensor of a different dimensionality. Typically, from here, again, assume that this is just one sample. So if you have a batch size or a set of samples, then you'd be computing the outputs for each of those samples. Typically, what I do when we go to a fully connected layer is we essentially vectorize this entire tensor, right? So someone may want to double check me about this, but I think if you perform a tensor multiplication, you can achieve the same thing as you vectorize that entire tensor and then just multiply it by the matrix. Because that matrix, with respect to the input and output, should have the same number of entries as the tensor itself that you'd be multiplying with, right? Does that make sense? Someone wants to fact check me on that. I'm pretty sure that's correct. Right. Okay. So say this is one sample. Right. All right. So what else? Supposing, say this output is 400. One sample has 496 entries, right? So that's like some number I get, or like it's in like the order of thousands, right? Keep in mind that every time I apply this neural network entry-wise, I'm also going to be applying that weight matrix to get a lower dimension. Say this is going to send us to the output, right? So say this is y, or what the class of the image is, say, for example. When I apply this transformation, I have to apply that on every single entry, right? So would it make sense to make a copy of every single time of every single weight matrix? Would that make sense for every single sample? Probably not. So what you could do is you could essentially apply this this matrix multiplication iteratively. Right? So aside from that, now by the way, in regards to the homework assignment, you came up with something along these lines. If I lost it. If you came up with something that's this or kept it as a matrix multiplication, you got full credit, just so we're all on the same page. Technically, from the work that I was referring to, if you had arbitrary tensors, I and j, can actually define vectors of indices if you're multiplying two tensors. So if you're going to generalize it, I, j, and k would all be elements of z. If I can draw the notation for integers of whatever order the tensor you're multiplying is. All right, so I think these would be as what we defined as it D, N, and M. We can make these capital D and M. All right, so those would be referring to the order of the tensor. Does that make sense? So instead of this defining a scalar, you just refer to it as a vector of vectors, or vector of entries, of indices referring to each dimension in that tensor. All right. That's what they had in the notes. Again, if I were to do this, I would just vectorize the entire output and just treat it as a vector instead of a higher dimensional tensor. Why complicate yourself if it achieves the same thing? Does that make sense? Did I lose one? Does anyone have any questions in regards to this? It's quiet, man. I need feedback. If I'm doing something wrong, you guys gotta let me know. Okay, so one last question before I inevitably let you guys go. Why would we take a derivative with respect to x as opposed to the weights if we want to train? Well, why would we take a derivative with respect to x? Does anyone know? All right. So for training, oh, do you know? Did you have any? Say that again. Oh yeah. Okay. So why would you? So if you're training, you'd take a derivative with respect to w, obviously, right? But if you're taking a derivative with respect to x, ultimately that would imply that maybe you'd want to change the input somehow. Okay? So why would we want to change the input? So one example, by the way, has anyone ever heard of adversarial attacks? So have any of you heard that buzzword before? So suppose we have so say this function defines our deep network, and x defines our input, which is a tensor. You can vectorize this. Y devotes our output. And say there's some like internal parameters in here that would define the intermediate activations and other features inside that network being computed. If we change, suppose we want to find the output that maximizes the output of some class. Say if we're classifying between dogs and cats, and I want to say, all right, give me an input that's going to give me the most dog in terms of the output, right? What you can do is you can actually fool networks to actually add a little bit of noise to the input to actually fool the network into classifying, to misclassifying. So if you want to be nefarious, you can apply a small amount of epsilon or a little slight perturbation in each of the inputs of your image to maximize the output of dog, when in fact it might be an image of a cat. So you could actually fool the classifier. So that would be one example. So if you're interested in doing something nefarious, you could do that. Also, if you want to make sure that your network, when you're working for Tesla, and your images are not being fooled by a stop sign, where a stop sign doesn't exist or something along those lines, you got to make sure that your networks are resilient to that, right? In addition, if you guys have heard of Deep Dream by any chance, so what you can do is you can actually, within the activations of the network, you can actually maximize those to elicit new images that look quite interesting, nevertheless. On the off chance you're interested in saving money on psilocybin and LSD, you can just do back propagation with respect to your input X. So if you guys get a chance, look up Deep Dream, and you'll find some really interesting outputs. So it's fascinating. It's really interesting what you can do. So, all right. So I think that's pretty much it. Again, you said you had a question?
That was the question.
Oh, okay. All right. Is that it?
Actually, I
Yeah,
have
that's
a
it.
question about the vectorizing the tensor.
Yeah.
So,
Yeah.
actually, I have this for a long time. I feel when you do that thing, when you do vectorize the tensor, you actually destroy all these structures, right?
Right. So that's one of the advantages of using knowing what kind of operation you want to apply. So if
Yeah,
you're
but I feel sometimes structure is kind of pretty important.
I agree, totally, 100%. So that's why, if you're interested, that's why the position is super important. That's why we have operations like convolutions, which actually take into account that locality.
So we don't vectorize the tensor at the beginning of the.
Probably not,
Okay.
right? But so I mean, I got to think about this. Is that if you could, do you have any insight? If you vectorize, do you lose anything if you vectorize the tensor?
I don't think.
Yeah, I got to think about that.
What do you say? Sorry.
I think, like for these things we are doing unit classification, we would like to generate a vector which is the number of the dimensional vectors corresponding to the classifications, right? If you have by
Number of
so
what? Number of what?
the dimension of the vector.
But when you resize the tensor.
Well, any other questions? Cool. All right, I think we should be good.